So today we're in part 2, 2.3. All right, so let's before we get into the heart of what we're doing today, let's recap a little bit. What we talked about the last couple of days. So we have a polynomial f of x. So this is a polynomial, and we're dividing by x minus k. The remainder theorem tells us, so we divide this polynomial by x minus k. The remainder theorem tells us that f, I'm going to do it the other way, the remainder equals f of k. So if we divide our polynomial by this something that looks like x minus k, whatever the remainder is f of k. If we plug k into our polynomial, the remainder would be the number we got out. If the remainder is 0, what does that tell us? F of k equals what? 0. The remainder. If the remainder equals 0, f of k equals 0. We said a couple of days ago that when our remainder is 0, when f of k is 0, there are several things that mean the same thing. So what are what did we say that were the things that were the same as saying f of k equals 0? X minus k is, what is it? A factor. X minus k is a factor of f of x. And just a quick reminder, when we say x minus k is a factor, if we factor our polynomial, we would have f of x equals, and x minus k would be one of these sets of parentheses we get when we factor this polynomial. So that would be one of the parentheses. X minus k is a factor. What was another way of another thing that was the same as saying x minus k is a factor? K is, what do we call it when we plug in a number and we get 0 in our function? It's a 0 of the polynomial. 0, the other way we say 0 is a root. K is a 0 or a root of f of x. What's another way of saying k is a 0 or a root? What's another way of saying f of k is 0? K is a solution. Very nice. K is a solution to f of x equals 0. And then there was one other thing. We have a factor. It's a 0 or a root. It's a solution to this equation. What does it tell us about the graph? It's an x-intercept. And remember, our x-intercept is a point. So we're going to say k, our point k comma 0 is an x-intercept. So all of these things, they all mean the same thing. These four mean the same thing. And that all happens when our remainder, when we do our synthetic division, is 0. So when the remainder is 0, we found a solution to our equation. We found a 0 of our polynomial. We found an x-intercept. So that's getting to 0, getting a remainder of 0 when we do synthetic division is a really important thing. One of the really nice things about polynomials is that we can figure out what the zeros possibly can be just by knowing the coefficients in front of our variables. That's all we have to know to figure out what possibly can be zeros of our polynomial. And that's what we're going to talk about next. How do we pick numbers? How do we pick these k's so that we might possibly get a zero of our polynomial? And that is called our rational zero test or our rational root test. So what the rational root test does is give us some numbers to try with synthetic division with. So we're going to say that f of x, we have this polynomial, a sub n, x to the n plus, we write this all out, n minus 1 plus dot dot dot, like we did a couple of times. This is a sub 1 x plus a sub 0. And for this we're saying that a sub 0 is not 0. So we have a number out here that's sitting by itself. What we're going to do is say that we're going to call a sub 0 p and a sub n q. And let's remember, if we're talking about a rational zero, what do we mean when we're talking about a rational number? What does a rational number mean? Makes sense when it talks to us? So what's the root of rational? What's the root of this word? What ratio? What's a ratio? What is it? A fraction. So what makes a fraction rational? What kind of number is in the numerator and denominator? What is it? I just can't hear what you're saying. That would be a proper fraction, but a proper fraction could still be rational. Yes. Denominator. So the denominator can't be 0. A rational number is when we have a integer on the numerator and denominator. Whole number in the top, whole number in the bottom. 1/2, 2/3, 5/7, 18/17. That's a rational number. So the rational root test gives us these fractions with whole numbers, positive and negative whole numbers in the numerator and denominator. So the rational root test says that the possible rational zeros of f of x are plus or minus factors of p over plus or minus factors of q. So we get a list of numbers. And we can test to see if they're zeros by doing synthetic division, see if our remainder is 0. Now, before we go on, what do we mean by a factor of p? What if p was 10? What's a factor of 10? 5? What's another factor of 10? 10? What's another factor of 10? 1? One more? 2. So we're listing those factors. Factors means it divides evenly. So this gives us numbers to test with synthetic division to see if our remainder is 0. That's what the rational root test does. So what I want to do is go through a couple of examples of using the rational root test, the rational zero test. So let's say we have our question says find the possible rational zeros of 3x to the third minus 20x squared plus 23x plus 10. So always when I do these kinds of problems, I always label my P and my Q. And then I make a list. So what are the factors of P? We just listed them, right? Of 10, plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. And what are the factors of Q? Three is prime, so what are the factors of 3? Plus or minus 1, plus or minus 3. So the possible rational zeros we just make a list of the numbers with p's in the numerator and q's in the denominator. So if 1 is in the denominator, we just get these numbers, plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. But we can also make these fractions with q as a denominator. So we get plus or minus 1/3, plus or minus 2/3, plus or minus 5/3, and plus or minus 10/3. So all of those are possible rational real zeros. Now if the problem just asks you to list the possible ones, it's just asking for this list. It's not asking you to do anything else. So those would be the possible numbers that could be possible rational numbers that could be zeros of that polynomial. So this gives us a list of numbers to try synthetic division with. So if we were trying to find our zeros, we would start plugging these numbers in with synthetic division and testing it. Try to get a zero remainder.
Do you have to do all of it? Do you have to test all of them?
No. And we'll talk about what we do next. Yes.
What happens if it's not trying to like class?
Well, these are the only possible ones.
No, but like for people.
Oh, then you have a huge list.
Good, we're not going to have that.
You will not have that. In the graduate course I took, we did a section on factoring polynomials, and there was one we did that was a 5th degree polynomial, and this number was 72 and this number was 24. So there was a long list. But we'll learn a couple of shortcuts to narrow it down, and then there are other shortcuts that are a little more complicated, but you can narrow it down a little bit to choose so you don't have to test as many. All right, so that's how we use the rational zero test. Get our p's and our q's, and get a list of numbers that we can test. All right, so let's look at how we're going to use it. Do a couple of examples of actually using it. Thank you, Ms. Voss. So let's find the solutions, find the real zeros of solve x cubed minus 7x minus 6 equals 0. So we want to solve this. So we're finding the solutions, finding the factors, finding the zeros. So here's my P, and here's my Q. Like that, the number in front of there. It's always nice when these are small numbers, and it's always really nice when one of them is 1. So what are the factors of P? Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. How about Q? Plus or minus 1. So we don't have any fraction we have to deal with. So these are the possible rational zeros. So all we have to test is plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And we're hoping that it's some of the early ones. Positive 1 and negative 1 are really easy to test. You don't even have to do synthetic division. I just try f of 1. F of 1, because when I plug in 1 for x, I just get 1. So I get 1 minus 7, which is negative 6, minus 6, which is negative 12. Not a 0. Let's try negative 1. Negative 1 is really easy to test. all I do is change the signs on the odd exponents. So I get -1 plus 7, which is 6, minus 6, which is 0. Yes?
Are you just plugging it in?
Yeah, I'm just plugging it in. Positive 1 and -1 are really easy just to plug in. So there's one of our zeros. So now we do synthetic division with -1. And we should get a 0 remainder.
Wait, can you just plug in, can you plug in like 2, 3, 6?
You could plug them in to test if they're zeros, but if you have a big polynomial, it's usually easier to do synthetic division and cubing and subtracting and all that kind of thing. All right, so let's set up our synthetic division here. So I put a 1 there. What do I have to put in here?
0.
A 0 for the x squared term, right? Good. -7, minus 6. Bring that down. And what should my remainder be here?
0.
Better be 0 or we've done something wrong. All right, we got a 0 remainder. We did it right. So this tells me I'm left with divided a cubic by a linear polynomial. So I should get a quadratic. And what can I do with this to find the other two zeros? This thing. Factor it. Oh, if it doesn't factor, what else could I do?
Plug in the other numbers.
Quadratic formula. So it's either going to factor, quadratic formula is going to give us our zeros. Does this factor? What does this factor to? X minus 3x plus 2. And we know the other 0 is -1. So we could say f of x, if it asks us to factor, f of x is x plus 1, right? From this. So our zeros are x equals 3, x equals -2, and x equals -1. And those are our solutions to that equation. Yes? Because this says that from this, x equals -1. So the factor is x plus 1 equals 0. So that's our factor. Because when we tried the positive one, f of positive 1 was -12. It wasn't 0. Yeah, we want it to equal 0. Yeah.
And so like what you get on the bottom there, it has to be what you found out for the factors of that.
Yes. So what we get on the bottom has to be, this would give us the rest of the factors of that polynomial. Yes.
So if you just like check all the other keys, like you see the other zeros.
Sure. So we got a 3 and a -2, and that's in our list here, right? But usually it's easier to do synthetic division than plug those numbers in and calculate.
So you just do that after talking.
Yeah, yeah. And our goal is always, when we're doing synthetic division, to end up at a quadratic polynomial so that we can factor or use a quadratic formula. And if we had a polynomial higher than third degree, we would have to do more than one synthetic division, because we want to get down to eventually where our polynomial is a quadratic, so we can factor or use a quadratic formula. So questions on the process we used there? Yeah.
So are you just saying it's easier to start with plus or minus
Yes.
1 when you're doing synthetic
Yeah.
division? Just find the zeros from there?
Yeah. Yeah. And we always hope that plus or minus 1 is one of them, because that makes our lives easier. If it's not, then we have to go to, I would then start doing synthetic division with plus and minus 2.
Okay.
Yeah, and you could do synthetic division with plus and minus 1. It's just not too hard to plug it in and calculate.
Okay.
All right, let's look at another example. Let's do a fourth degree polynomial where we have to do more than one synthetic division. Find the real zeros of, I'm going to say of x to the fourth minus 3x to the third plus x minus 3. And I'm always happy when our p's and our q's are prime because they don't have very many factors. There's p, there's q. So our factors of p here are just plus or minus 1, plus or minus 3. Factors of q are just plus or minus 1. So our possible rational real zeros are just plus or minus 1, plus or minus 3. So I suggest just plugging in positive and negative 1 to see if it works. So f of 1 is 1 minus 3, which is negative 2, plus 1, which is negative 1, minus 3 is negative 4. So that's not a 0. Yes? Right. Well, it'd be 0x squared, so it would just be a 0 in there anyway. All right, let's try f of negative 1. Change the sign on the negative x, or on the odd exponents. So 1 plus 3 is 4. Minus 1 is 3. Minus 3 is 0. So there's one of our real zeros, is f of negative 1. Now we can set up our synthetic division. So I'm going to put a negative 1 there. I'm going to put a 1 for the x to the fourth, a 0 for the x to the third, a minus 3, a 1, and a minus 3. Bring that down to my synthetic division. We get it.
Not put a 0 for the x. We already have one of those. Would it be for x squared and put 0?
Did I put it in the wrong place?
Yeah.
No, I did. Nice catch. Thank you. Minus 4. We get there. 4, 4, and we better get a 0 remainder here. All right, so we get a 0 remainder. So I have divided a fourth degree polynomial by x plus 1. So what am I left with here? I reduce the power by 1, right? So this is still a third degree polynomial. I need to find the factors of that third degree polynomial. So what do I do to factor that? Well, these numbers, a plus or minus 1 and plus or minus 3, those are possible rational roots of this. I've only divided out one of them. So whatever's left has to divide whatever's left when I do the original division. So if I divide 20 by 2, the other factors of 20 are 5 and 10. I can still divide whatever's left by 5 or 10, right? Same idea here. So what do we want? So this gives us a cubic polynomial. We want to get it down to a quadratic polynomial. So what number do we want to test with synthetic division now? We already tested plus or minus 1, so what would be the next easiest one to test from our list? How about 3? And I'm just going to do that synthetic division. I just picked one of the other possible rational real zeros, and I'm going to do the synthetic division just right there. I'm not going to rewrite it. I'm just going to do it right there. So I'll do the synthetic division there. And that turns out to be another real zero. So far we've gotten x equals negative 1 and x equals 3. If 3 didn't work, then I would have to try synthetic division on this piece with negative 3. if we had a longer list and we tried a couple and they didn't work, just have to keep going and trying until you get one that works. So I started with a 4th degree, ended up with a 3rd degree polynomial. Now I have a quadratic. So I have x squared minus x plus 1. Can we factor this? Yes? No? What would this? How do we want to factor this? X minus 1. Does it work? So if this doesn't factor, what would we do after we try to factor this? If we can't factor, what always works on a quadratic? A quadratic formula. So if we plug this into the quadratic formula, x equals negative b, the square root of b squared, 1 minus 4 times 1 times 1 over 2a. 1 minus 4 is negative 3. Square root of negative 3 is imaginary. So this doesn't give us a real, this one doesn't give us real roots. So our real roots of this polynomial are x equals negative 1 and x equals 3. And if it asks us to factor this, we could say that x to the 4th minus 3x to the 3rd plus x minus 3 equals x plus 1 times x minus 3 times x squared minus x plus 1. So that would be the factorization of this polynomial. So we found our real roots, we found our factorization. Yes? X equals 3 came from this one. Because when I did my synthetic division here, I got a 0 remainder. Well, this part, this piece gives us no real root. So from this, the part that's left over after we found 1 and 3, we get no real roots from this part. So we already found the negative 1 and the 3. Those are real roots. But what's left doesn't give us any more. So the only two are negative 1 and 3. Because this possibly could have 4 real roots, right? But only 2 of them are real. The other 2 are imaginary. All right, questions there? So our goal when we do the synthetic division, we want to find a 0 remainder, and eventually we want to get our degree of our polynomial, whatever we're left with, down to a quadratic where we can factor or use a quadratic formula. So if we have a 5th degree polynomial, and we're finding all the real zeros of a 5th degree polynomial, we're going to have to do synthetic division 3 times, and then get down to a quadratic polynomial. If you had a 6th degree, you'd have to do synthetic division 4 times, get down to a quadratic polynomial, and so on and so on. But the P's and the Q's give you numbers to test with your synthetic division. All right, let's talk about one more thing. One more way that we can narrow down our list of things to test. And that is Descartes' rule of signs. Descartes' rule of signs just gives us a way to eliminate some possibilities from our list. And it sounds, when we write it out, it sounds more complicated than it really is. So we have f of x, and this is a polynomial. We have two conditions here. The number of positive real zeros, and notice we're saying just real zeros now, not rational. The number of positive real zeros of f of x equals the number of sign changes in f, and we'll talk about what that means. Or less by a even number. And we'll talk about what we mean by the sign changes and everything in just a second. It's really easy. It sounds complicated. Descartes' rule of signs is extremely easy. The number of negative real zeros. Is the number of sign changes of f of negative x. Or less by an even number. All right, so let's talk about what we mean by the sign changes and this whole business about even numbers. Really easy idea. So let's say we have f of x equals 2x to the third minus x squared plus x plus 4. For the number of sign changes, all we're doing is counting how many times the signs in front of our numbers here change from positive to negative or negative to positive. So here we have a positive 2, and that changes to negative. So that counts as a sign change. Here we have a negative, and that changes to positive. That counts as a sign change. Here we go positive to positive. That doesn't count as a sign change. So Descartes' rule of signs says we have two sign changes. So we have 2, or we go down by an even number, we can go down by 2 or 0 positive real roots. So let's say we do our synthetic division. Let's say we test positive 1. That turns out to be a solution. We do synthetic division with 3. That turns out to be a positive solution. Well, Descartes' rule of signs says those are the only two positive solutions. The rest can't be positive. So we don't even have to check any more positive numbers. That's how we use Descartes' rule of signs. Yes? No, so it doesn't change signs. So we're counting how many times the numbers in front here go from positive to negative or negative to positive. So here's positive to negative, so that counts as 1. Negative to positive, that counts as 1. And these are the same, so we're not counting it as a change. So this polynomial has either 2 or 0 positive real roots. F of minus x. Really easy to find f of minus x. Change the signs on the terms with the odd exponents. Minus 2x to the third minus x squared, this is odd, minus x plus 4. And now I'm going to count those sign changes. Don't have one there, don't have one there, I have one there. We have one sign change. So we have 1, and I can't go down by an even number, so we just keep going down by 2s. I can't go down by 2, I get a negative. So we have 1, negative real zero. So let's say in this problem we tested f of negative 1, and that turned out to be a 0. That can be the only one. The rest have to be positive. So this lets us narrow down our search if we're doing our looking for our p's and our q's. Mm-hmm.
How about 2 or 0? Like,
So we can go down by 2s. So we can always reduce the number by 2s.
so if you have 4,
It would be 4, 2, or 0. Go to 6, it would be 6, 4, 2, or 0. And we'll talk about why that is in the next couple of days.
but if it's 1,
We can't go down by 2 because then we get to a negative number. We can't have negative 0. If it were 3, it could be 3 or 1. We go down by 2 each time, so it could be 3 or 1. All right, let's look at another example of how we use Descartes' rule of signs. So Descartes, famous mathematician, he came up with Cartesian coordinates, the xy plane. Mathematician tried to teach Descartes' rule of signs to a horse. You know why the horse wouldn't learn it? He was trying to put Descartes before the horse. All right. Where's my other example? This is my other example. F of x. All right, we want to figure out how many positive or negative real zeros here. We're going to use Descartes' rule of signs. So sign change there. Sign change there. No other sign changes. And let me change this. I want this to be a negative 1. So there's a sign change. So we have 3 sign changes. So we have 3 or 1 positive real zero. Let's look at f of minus x. I'll change the signs on all the odd exponents. This one's even, so it stays the same. This one's odd, so that changes signs. How many sign changes there? No sign changes. They stay negative the whole time. So there are no negative real zeros. So this tells us if we got our list of p's and our q's, we don't even have to try any of the negative numbers. We only have to try the positive numbers. So Descartes' rule of signs would tell us don't even try the negative numbers. So that cuts our possibilities in half. Yes?
Which ones do you put?
The signs in front of the odd powered exponents. So I just change the sign in all the odd powered exponents. So this is odd, so I change the sign there, and this is odd, so I change the sign there. So Descartes' rule of signs just lets us narrow down our search. All right, one last question for you guys, then we'll be done. What if we had a polynomial that looked like this? X to the 4th plus 3x squared plus x, and the problem was to factor or find all the real zeros or whatever else. What is, if I didn't do anything to this first, what is my p here? 0. So remember in our rational zero test we said that this number couldn't be 0 to use our p's and our q's. So what would I do with this one in order to find our zeros? Can I rewrite this somehow? What can I do here? Factor out an x. Well, we factored out an x, so what is one of the zeros of this polynomial? X equals 0. And then we would do synthetic division on this part. So if we have a common term, we can factor that out so we can do the synthetic division. And this one would be really easy. What are the only two possible rational real zeros of this one? Plus or minus 1. So we could try those and see what we get. And we could use Descartes' rule of signs. How many positive real zeros would this have? How many sign changes do I have here? 0. No sign changes. So the positive real zeros have to be negative. Or sorry, so there are no, I'm sorry, the positive real zeros, that didn't make sense. There are no possible positive real zeros. So if they're real zeros, they would have to be negative. All right.
So for like this problem,